Hello everyone who is watching this record of my presentation. My name is Pozhylenkov. I am a PhD student from the Odessa National Mechnikov University, and today I want to discuss about the stress state of a rectangular domain with mixed boundary conditions. So here it is, a structure of my today's report. Firstly, I want to briefly discuss about the literature review. Second, I will introduce the problem statement that I am working on, show to you how I have solved this problem, what mathematical approach I have used, how I have found the solution in the transforms domain. Next, I will show you the integral equation that I have got and how I will solve it. Next, it will be some numerical results, and the last one, some conclusion notes. The problem of the elastic rectangular domain is not a new one, but unfortunately a lot of unsolved issues remain. This problem was considered and resolved in the different statements important to the engineering applications as with the help of the analytical methods, so and with the numerical ones. The well-known paper first was one of the pioneer paper in this direction. The solution of the plane thermoelasticity problem for a rectangular domain was constructed with the help of a new solving method. This method permits the construction of an analytical solution corresponding to Saint Venant principle in the form of trigonometric series expansion using a complete orthogonal set of the eigenfunction and associated functions. These investigations were successfully continued by the Tokovoi in the second paper. To the direction one can reference the papers where the boundary element free method was applied to two-dimensional problems of elasticity. This method is a direct numerical method, and it was stated at the third paper, gives the higher computational accuracy. For example, at the paper 4, the discussion of the conditions type necessary for the penalty method to provide a basis for the stable and convergent finite element schemes is proposed. But if one need to provide the calculation of the stress at the rectangular domain in the neighborhood of the angular points, the numerical method loses their efficiency as it's known. So the main idea of my research is to find the exact and the analytical solution for the sum of the problems of the elasticity for the rectangular domain. And the novelty of the presented solution is to apply methods which were stated by the Popov and described at the paper 5. So here we have the elastic rectangular domain. We consider it in such way that x changes from 0 to a and y changes from 0 to b. The first equation are the well-known equations of the elasticity that is stated the two-dimensional problem. Our domain meets a load at the upper face of the domain. It's equation 2. The lower base at the conditions of the ideal contact. It's equation 3. The right side also at the condition of the ideal contact. It is equation 4. And the last one equation is equation 5. It is the left side of the domain has a zero displacements. To solve it, I have applied the Fourier transforms which can help to rewrite our stated problem in the one-dimensional field. Here is presented the detailed representation how I have applied this method. It is equation 6. You can see that I have applied two different Fourier transforms for the displacements functions but with the same eigenvalue. So as a result we will have a one-dimensional problem that I have derived in the matrix vector representation. It is presented in equations 7 from 7 to 10. To find a solution for the one-dimensional boundary problem, I have used a fundamental solution matrix, which is solution of the homogeneous problem. I have found it in such form which is presented in the equation 11. Where to calculate such integral, I have used well-known residue theorem. So as a result, we have two parts of the fundamental solution matrix. It is equations 13 and 14. Thus, we have found the solution of the homogeneous one-dimensional vector boundary problem. With the help of the fundamental solution matrix, I have found the fundamental basis solution matrices that you can find it using such representation, it's equation 15, and applying the boundary conditions to find the elements of the matrices C1 and C2. Finally, using the fundamental basis solution matrices, we can get the Green's matrix in the such representation, it's equation 16. So the exact solution in the transforms domain will have such representation in the equation 17. So the final exact solution of the displacements of our problem we can find just applying the reversible Fourier transform. Here it is the final representation described in the equation 19. Unfortunately, in the final exact solution we still have some unknown parts. It is the function fc described in equation 21. So find it, we have derived an integral equation applying such boundary condition to our displacements, described in equation 20. This integral equation was solved with the help of the orthogonal polynomial method and was reduced to the infinite system of linear algebraic equations. Here it is some numerical results with the stated load function, but is for the analogous problem where we have the conditions of the ideal contact for both lateral sides, not only on the one. On this picture you can see the displacement function v with such load function px. Here it is presented the displacement function u for the same load function like on the previous slide. The proposed method was applied to solve the first main elasticity problem for a rectangular domain. It reduces the problem to the single equation. The orthogonal polynomial method was used to derive the solution. The future development is connected with non-stationary elasticity problem for a rectangular domain where proposed solving method will be applied. Thank you for your attention.